This is a charging connector for an electric truck. It must remain manageable enough for a driver to lift, insert into the vehicle inlet, and lock by hand. Yet, the current inside it can reach thousands of amperes. IEC. Technical specification 63379, published in 2026, covers megawatt DC connectors, inlets and cable assemblies rated at up to 1500 volts DC and 3000 amperes. Multiplying those upper limits gives 4.5 megawatts, but not every connector, vehicle or charging session operates at both limits simultaneously. The challenge is carrying that power through a flexible cable and detachable metal contacts without overheating the conductors, contact surfaces, or insulation. A tiny increase in resistance can turn one location into an intense heat source. So how does MCS contain the current, remove the heat, and protect the person standing beside it? The Megawatt Charging System, or MCS, is intended primarily for vehicles with very large batteries, especially heavy-duty trucks. A long-haul truck carries substantial loads, travels hundreds of miles, and must return to service on a practical schedule. Passenger car charging power could leave it idle for too much of its operating day. An MCS connector is larger and heavier than a passenger car plug, but is still designed for manual handling. Its housing provides a grip, protects insulation, and keeps internal components aligned as it enters the vehicle inlet. Inside are two main DC paths, positive and negative. Large conductor cross-sections reduce resistance. The assembly also includes protective grounding, communication contacts, and components that confirm correct insertion and locking. Keying. The power contacts must establish a stable conducting area under controlled pressure. Misalignment, contamination, wear, or lost pressure can reduce the true contact area and raise interface resistance. Actively cooled designs add coolant paths along the cable and connector assembly. Architectures vary by manufacturer. Coolant absorbs heat from conductor and connector regions, returns to the station, and transfers energy through a heat exchanger. A pump maintains flow while a fan or secondary loop rejects heat. This is more than an oversized plug. It is a high-power electrical device, a thermal transport system, a mechanical lock, and a communication boundary between truck and station. The main enemy follows a short equation. Resistive heat equals current squared times resistance. The dangerous word is squared. If resistance stays constant and current doubles, heat increases fourfold. If one point has only 0.1 milliohm of resistance, 3000 amperes would generate about 900 watts there. At 1 milliohm, the theoretical loss becomes 9 kilowatts. That energy is not reaching the battery. It is becoming heat inside a small electrical path. A thicker cable lowers resistance, but adds metal, mass, stiffness, and bending radius. It also increases the load on the connector and inlet. The detachable interface is harder. Cable conductors are continuous, but the connector is repeatedly inserted and removed. Each cycle can add wear, dirt, misalignment, or sideways loading from the cable. Can change how the metal surfaces press together. At the U.S. National Renewable Energy Laboratory, connector and inlet combinations were evaluated at several currents, reaching 3000 amperes with active cooling. After thermal steady state, devices were loaded with 100 newtons in multiple directions to examine misalignment. A connector may work when perfectly aligned yet must maintain an acceptable thermal behavior, while a heavy cable pulls against it. More cooling can support current but adds hoses, pumps, exchangers, sensors, and leak management requirements. More conductor reduces resistance but makes the cable heavier. Greater contact force may reduce resistance but increase insertion effort and wear. The engineering problem is balancing all three, while preserving manual operation. The solution is coordinated control of the electrical path, thermal path, and connection state. Higher voltage transfers more power without raising current by the same proportion, because power equals voltage multiplied by current. But it also demands appropriate insulation, spacing, materials, and protection. Voltage cannot increase without limit. Current travels through conductors with sufficient cross-section, i.e. Flexible cables generally use many small metal strands, instead of one rigid bar. This preserves bending ability, but flexibility, resistance, strength, and mass remain linked. At the connector-to-inlet interface, the goal is low and stable resistance. Contact geometry, pressure, alignment, surface condition, and locking all matter. One poorly seated contact can create a local hotspot, while the rest of the cable remains cooler. In an actively cooled assembly, heat moves from the conductor through intermediate materials toward a coolant channel. Liquid absorbs the energy, returns to the station, and passes it to another cooling loop or heat exchanger. NREL's test setup used water with a nominal 30% propylene glycol concentration to receive heat from actively cooled equipment. It supplied separate nominal flows to the connector and inlet. Those values describe the test bench, not a universal MCS recipe. Manufacturers may use different passages, coolants, pumps, and exchangers. Cooling does not eliminate resistance. It moves heat already generated. If a contact interface is seriously degraded, more coolant may not correct the cause. The third layer is monitoring. The system establishes that the connector is inserted, locked, and communicating with the vehicle before high voltage is applied. Vehicle and station agree on conditions compatible with the battery, cable, and connector. During charging, temperature and system state measurements reveal heating trends. If temperature rises too quickly, the controller can reduce current. If a safety condition is exceeded, charging must stop before removal is allowed. At NREL's 4th MCS evaluation event, one criterion kept steady-state DC contact temperature rise below 60 Kelvin, together with a 100 degrees Celsius overall test limit. These were criteria for that evaluation and its reference documents, not universal operating temperatures. The system therefore controls current, according to resistance, cooling capacity, and the actual condition of the connection, rather than waiting for the housing to become dangerously hot. The driver inserts the connector. Mechanical geometry aligns the contacts, and the lock holds them in position. Control contacts confirm connection, and allow the vehicle and station to communicate. High voltage is not applied merely because metal surfaces have touched. After validation, vehicle and station establish charging limits. In an actively cooled system, the pump establishes coolant flow. The controller checks thermal and connection status before the contactors close and current rises. DC current travels through the positive conductor, enters the battery, and returns through the negative conductor. Resistance converts part of the energy into heat. Large conductors reduce resistance. Stable contact force prevents concentration at the interface. Coolant carries heat toward the exchanger. Sensors close the feedback loop by tracking temperature, lock state communication, and component limits. If temperature remains permitted, high power charging continues. If heat accumulates faster than the system can reject it, current is reduced. Because Joule heating depends on current squared, even a moderate reduction can cut heat substantially. If the connection becomes unstable, temperature exceeds a limit, or another safety condition is lost, contactors open the high power path. Only after voltage and system state are safe can the connector be unlocked. No single component enables megawatt charging. Conductors, contacts, coolant, locking hardware, sensors, and control must operate as one system. MCS can carry thousands of amperes not because it is immune to heat, but because it reduces where heat is produced, transports unavoidable heat away, and reduces or interrupts current when conditions are unsafe. It is not simply a larger cable. It is an electrical, thermal, mechanical, and control system compressed into a connector a person can still handle. Controlling tiny fractions of an ohm determines whether megawatts enter the truck or remain as heat inside the plug.